Okay, folks, welcome back to Physics with Captain Rod. The purpose of this discussion is to talk about what's referred to as the ideal gas law. So let me talk about what we're looking at here. This beautiful picture is representing a piston cylinder assembly. And all of these little dots in here are supposed to be molecules within it, molecules in a gaseous state. So some things to remember about pictures like this is, one, the number of molecules. These are awfully large numbers. These are numbers like, order of magnitude wise, typically like, I'll just say approximately 10 to the 23rd power. So I'm drawing just, 30 or so for visualization purposes, but in reality, you're talking about much, much larger numbers. All right, second, another important thing to consider is size. Of course, you can never see molecules. They're thousands of times smaller. Another important thing to realize is the average speed. It's not uncommon to see numbers like, 10 to the 5th power, like 100,000 meters per second. I'll just put approximate 10 to the 5th meter per second. That's not a super uncommon molecular speed. So these things are buzzing around here pretty fast. Now, what I call the thermodynamic variables are pressure, volume, and temperature. I'm going to go ahead and kind of define these things real quick here for this video. Pressure is defined as force per unit area. This is not my primary video for defining this. I'll just make that quick. Volume is just like you would think it is. It's, volume typically measured in cubic meters. And then temperature is defined as a measure of molecular kinetic energy. All right. And the one more variable we're going to talk about that's linked to this is the number of moles in this container. And that's going to be N, where 1 mole of anything is equal to Avogadro's number. I usually put N sub A here, of the anythings, which is 6.022 times 10 to the 23rd particles. Should have probably chatted about that a little bit before we got this rolling, but I'll do so now. So the idea of a mole is a counting number. So for example, you can buy Pepsi by the 6-pack or maybe the 12-pack, and you can buy bottle rockets by the gross, which is 144. Well, a mole of bottle rockets would be 6.022 times 10 to the 23rd bottle rockets. The reason it's so absurdly large is because, molecular numbers, these are the types of numbers you have in just like a 2-liter container of air. Now, these variables, the pressure, volume, temperature, and the number of moles, are related by what's called the ideal gas law. So I'm going to write it down and then chat about it. So the ideal gas law is pressure times volume equals nRT. Where again, the P is the pressure, and by the way, it needs to be in what's called an absolute pressure, which is force per unit area. The volume is typically, is the volume measured in cubic meters. The N is the number of moles. R is called the ideal gas constant. Its numerical value is 8.314, has units of joules per mole Kelvin. And the T is your temperature in kelvins. So the ideal gas law is just a experimentally determined law. There's no deriving it. And it's the law that basically relates pressure, volume, number of moles, and temperature. A very important thing about the ideal gas law is both the pressure and the temperature need to be absolute quantities when using this law. Now, as far as homework problems having anything to do with the ideal gas law, these homework problems typically come in what I call 2 states. I call them state 1 problems and state 2 problems. Here's what I mean by a state 1 problem. I'm sorry, not state 1. I usually call them a type 1. Type 1 ideal gas law problem. Okay? You're given 3 of the 4 things. You're given 3 out of 4, and you find the 4th. There's almost nothing to it. The only thing you need to do is make sure that you write out the ideal gas law, and make sure that when you put in the pressure and the temperatures, they are in absolute quantities. Then you have what I call a type 2 problem. In a type 2 problem, you're looking for a change in state. I'll put change in state. Now, what do I mean by that? Well, in this piston cylinder assembly, if the piston moved to the right, if we moved this thing to the right, we would be compressing the gas, and then the temperature, the volume would go down, pressure and temperatures would tend to go up. Or maybe we heat the gas, increasing the temperature and pressure and so forth. But any changes in those variables represents a change in state. And the thing is about the ideal gas law is if I have two different states, like I'm going to call them state 1 and state 2, the gas law applies at both states. So we can write out like P1 V1 equals N1 R T1. And P2 V2 equals N2 R T2. I'm just tacking 2's onto all the variables to represent the different states, or the two different states. And if you solve this for R, and you solve this for R, and set the two terms equal to one another, you get P1 V1 over N1 T1 equals P2 V2 over N2 T2. And this is where you basically want to start if you have a problem where you identify a change in state. All right, so that's my ideal gas law deal in 10 minutes or less. Let me kind of review that. The ideal gas law equation is this. Whoops. That is a what I'll call first principle equation. There's no deriving that. For any homework problems or any physics problems you're dealing with, what you want to do is identify whether there's a change in state or not. And here's what I mean. Look at all the variables: pressure, volume, number of moles, and temperature. If none of them are changing in the problem, it is what I call a type 1 problem, and all you do is write down this law, and it'll basically have to boil down to here are 3 of the variables, what's the 4th? Make sure that you put the pressure and temperatures in their absolute form. If there is a change in state, right, if you do identify a change in state, meaning you have a problem and it says something about the volume changing or the temperature or the number of moles or the pressure or any combination thereof, then you write the gas law out in this form and start figuring out what goes there, what goes where, and solving for your unknowns. It's quite common in these problems for some things to be constant. For example, in a constant volume problem, the volumes would cancel. Or maybe a constant temperature problem, these would cancel. Or a constant mole problem, these would cancel, and so forth. So, not the greatest video I've ever done on this stuff, but that should be enough to give you an idea of how to get rolling on these problems. So, I think I'll make different videos to help with the individual homework problems. Have a great day.